quantum gravity. The big unsolved problem.
The big one. And one of the key ideas that emerged from trying to combine quantum mechanics and gravity comes from Richard Feynman's sum over histories approach to quantum mechanics.
Sum over histories? What's that?
Well, in classical physics, if you throw a ball, it takes one definite path from your hand to where it lands, right? Determined by gravity and initial velocity.
Yeah, parabola.
Right. But Feynman proposed that in quantum mechanics, a particle doesn't take just one path from point A to point B. Instead, it simultaneously explores every possible path it could take through space-time.
Every path. Even crazy zigzag ones.
Even utterly crazy ones. And the actual outcome we observe, the probability of it ending up at point B, is calculated by summing up contributions from all these possible histories, weighted appropriately. It's a fundamentally probabilistic view.
Wow. Okay, so particles explore all possibilities. Yeah. How does that connect to the beginning of the universe and this weird imaginary time thing I've heard about? That sounds like something straight out of science fiction.
It does sound sci-fi, but imaginary time is a perfectly well-defined mathematical concept, and it turns out to be incredibly useful, almost essential, for making these quantum gravity calculations, particularly Feynman's sum over histories, actually work without blowing up into infinities.
So what is imaginary time, mathematically?
Okay, think about regular numbers on a number line. Imaginary numbers involve the square root of -1, which we call I. They lie on a separate number line, perpendicular to the real number line. When we talk about imaginary time, we're essentially performing a mathematical trick, where we treat the time coordinate as if it were multiplied by I. We rotate the time axis in a mathematical space.
You rotate time, like it's another direction in space.
Mathematically, yes. So imagine you're navigating a map. You can go north-south, that's one real spatial dimension. You can go east-west, that's another real spatial dimension. Up-down is the third.
Right, our three spatial dimensions.
And then there's real time, moving forward, like a path marking out events chronologically. But what if, mathematically, you could introduce another direction, let's call it imaginary time north, that behaves mathematically just like one of the spatial directions.
So it's like adding a fourth spatial dimension, but it's related to time through this I.
Exactly. In this mathematical framework of imaginary time, the usual distinction between time and space completely disappears. Time becomes just another spatial dimension. Space-time effectively becomes Euclidean, which is like our familiar flat three-dimensional space that obeys Pythagoras' theorem, but now with an added fourth imaginary spatial dimension linked to time.
And why do this mathematical trick? What does it achieve?
It achieves something remarkable. It allows us to perform the sum over histories calculation for the entire universe, considering all possible shapes and evolutions of space-time, without encountering the problematic singularities that plague classical general relativity in real time. The maths becomes much better behaved.
So you calculate things in this imaginary time, Euclidean space.
Yes, you calculate the probabilities for different universe histories in that framework. And then, crucially, you can mathematically rotate back to real time to work out what the most probable history of the universe, the one we actually experience, would look like.
That is a truly provocative thought.
Yeah.
That maybe this Euclidean space-time, the one with imaginary time where space and time are interchangeable, might be the more fundamental concept.
Yeah.
And what we think of as real space-time, with its clear distinction between space and a forward-flowing time, is just like a figment of our imagination, a model we create to make sense of our observations within that deeper structure.
It definitely blurs the line between mathematical constructs and physical reality in a profound way, doesn't it? It suggests that maybe the universe at its most fundamental level, particularly at its beginning, is simpler and more geometric than our classical intuition allows.
Mm-hmm.
In this framework, using imaginary time, the universe wouldn't necessarily begin at a sharp point, a singularity. Instead, it could be described as a self-contained, finite but unbounded structure, like the surface of a sphere.
Finite but unbounded. Like you can travel forever but never hit an edge.
Exactly. Just like you can walk forever on the surface of the Earth without falling off an edge because it curves back on itself. But the Earth's surface area is finite. The idea is that the universe in imaginary time could be like that finite in duration, but with no beginning or ending boundary, no singularity where things break down.
So no sharp starting point, it just is.
That's the implication of the no boundary proposal that emerged from these ideas. It removes the problem of the initial singularity and the need to specify arbitrary initial conditions.
Okay, let's talk more about time. We all feel time moves forward, right? The past is fixed, the future is open, we remember yesterday, we anticipate tomorrow. But why? Does time itself have a built-in direction? Do the fundamental laws of physics actually care about past versus future?
That's one of the deepest and most fascinating questions in all of physics, and the answer is surprisingly complicated. At their most fundamental level, most of the known laws of physics actually don't distinguish between the past and the future.
Really, they don't care which way time flows.
For the most part, no. They exhibit what's called time reversal symmetry. If you were to take a movie of any physical process governed by gravity or electromagnetism or the strong nuclear force and run the movie backwards, the reverse sequence of events would also obey the same fundamental laws. A planet orbiting a star could orbit the other way. Colliding particles could fly apart in reverse.
So the basic laws are time symmetric.
Largely, yes. There are some very subtle exceptions involving the weak nuclear force and certain particle decays related to symmetries called C, charge conjugation swapping particles antiparticles, and P, parity mirror reflection. But even those seem to obey a combined CPT symmetry, including T for time reversal. So fundamentally, the laws themselves don't seem to have a preferred direction for time.
So if you met an alien from an antimatter planet, and they held out their left hand, you probably shouldn't shake it, right? Because you'd both disappear in a tremendous flash of energy.
Definitely not recommended. Bad handshake.
But the fundamental laws describing that catastrophic handshake would look pretty much the same whether time was running forward or backward during the explosion.
Chuckles. Broadly speaking, yes. The underlying laws are remarkably symmetric in time. Yet, our everyday experience screams that there's a difference. We clearly perceive time flowing in one direction. We remember the past, not the future. Broken glasses don't spontaneously reassemble themselves on the floor.
Right. So where does this obvious arrow of time come from, if not from the fundamental laws?
This apparent paradox leads physicists to talk about three distinct, though interconnected, arrows of time that give time its perceived directionality for us.
3 arrows. Okay, what are they?
The first, and probably the most fundamental for explaining our everyday experience, is the thermodynamic arrow of time.
Thermodynamics again. Back to entropy.
Back to entropy. This is the direction in which disorder, or entropy, increases in a closed system. It's the most widely accepted physical explanation for why time seems to have a direction. The second law of thermodynamics dictates that total disorder always tends to increase over time. Things naturally go from ordered states to disordered states.
Right, like my Thali example. The carefully arranged plate of food before the meal versus the mixed up, messy plate after. You always remember the ordered state at the start, not some hypothetical future state where the food magically unmesses itself back into neat piles.
Exactly. Or think about a jigsaw puzzle. There's only one perfectly ordered state, the completed picture, but there are an enormous number of disordered states, pieces jumbled in the box. If you shake the box, you're overwhelmingly likely to end up in a more disordered state, simply because there are vastly more ways for the pieces to be disordered than ordered.
Nature just favors the mess because there are more ways to be messy.
Precisely. If a system starts in an ordered state, it will almost certainly evolve into a more disordered one. So the thermodynamic arrow points from order to disorder.
Okay, that's arrow number 1. What's the second?
The second arrow is the psychological arrow of time. This is our subjective sense of time passing, the direction in which we remember the past but not the future.
Our feeling of time flowing.
Yes. And what's fascinating here is how intimately it seems to be connected to the thermodynamic arrow.
How so?
Well, think about forming a memory. In a sense, you're creating order in your brain, right? You're arranging neurons or storing information in a specific pattern. That's a decrease in entropy locally. within that part of your brain.
Okay, creating order in the brain.
But the process of forming that memory, all the chemical reactions, the electrical signals, requires energy. And using that energy inevitably dissipates waste heat into your surroundings. This dissipation of heat increases the total disorder, the total entropy in the universe by a much larger amount than the small decrease in entropy caused by ordering your memory.
Wow. So even the act of remembering the past contributes to the overall increase of disorder in the universe.
Exactly. For our brains to function and form memories, we must operate in a way that aligns with the thermodynamic arrow. We must increase total entropy. So, our psychological arrow, the direction of our memory, naturally aligns with the direction of increasing universal disorder.
So, as the source puts it, disorder increases with time because we measure time in the direction in which disorder increases. You can't have a safer bet than that. It sounds almost circular, but deeply true. Our experience of time is defined by this fundamental tendency towards disorder.
It is a profound, almost self-defining relationship. Our perception is locked into the universe's tendency towards messiness.
Okay, thermodynamic arrow, psychological arrow, what's the third?
The third arrow is the cosmological arrow of time. This is simply the direction of time in which the universe is expanding rather than contracting.
Just the fact that the universe is getting bigger?
Yes. And the argument is that for intelligent beings like us to exist and be able to observe the universe and ponder these questions, all three of these arrows, thermodynamic, psychological, and cosmological, must point in the same direction.
Why?
Well, we've seen the psychological arrow depends on the thermodynamic arrow. And the argument, especially if you accept the no boundary condition idea we discussed, is that the thermodynamic arrow itself is linked to the cosmological arrow. A universe that started smooth and ordered, as the no boundary condition suggests, and is expanding naturally allows for disorder to increase over time. A contracting universe might have different implications for entropy, so intelligent life can likely only arise and persist in an expanding phase where disorder can grow, allowing for complex processes like memory formation.
So all three arrows have to point the same way for us to be here. That's neat.
It ties our existence to the fundamental evolution of the cosmos itself.
Okay, this brings us back to that really profound idea you mentioned, tied to quantum gravity and imaginary time. What if the universe simply had no beginning in the way we usually think? No sharp edge, no starting gun, no singular moment of creation.
This is the essence of the no boundary condition proposal for the universe. It's an attempt to use quantum gravity to resolve the classical dilemma.
What was the classical dilemma again?
In classical general relativity, based on the singularity theorems, the universe either had to have existed for an infinite time in the past, which runs into problems, like why hasn't it reached thermal equilibrium? Or it must have had a beginning at a singularity, that point of infinite density where the laws break down.
And the singularity is where classical physics gives up.
Exactly. It means classical theory cannot explain its own origin or the initial conditions. It needs something external or just accepts it as a brute fact.
And quantum gravity offers a way out.
It offers a potential way out. By incorporating quantum principles, particularly when describing space-time using those Euclidean space-times with imaginary time.
Yeah, where time acts like space.
It becomes mathematically possible for space-time to be finite in extent, but have no singularities that form a boundary or an edge. It can be smoothly curved back on itself.
Okay, like our Roki or Ladue analogy. Imagine the universe is like the surface of a perfectly round roti. Maybe.
Go on.
It's finite, right? It has a definite surface area. But it has no sharp edges. No special starting point, no end point. You can trace your finger over it forever, and you never hit a boundary or a singularity where the roti breaks down. It's perfectly smooth and self-contained.
That's precisely the visualization, just extended into more dimensions than we can easily picture. The universe, in this view, could be finite in imaginary time, but have no beginning or ending boundary, just like the surface of the Earth has no edge.
And why is this idea so revolutionary? What does it imply?
It's revolutionary because it means there might be no need to specify how the universe began at some boundary. There's no edge where initial conditions need to be set. There's no need to appeal to an external creator or some mechanism outside the universe to kick things off. There are no singularities where the laws of science break down. The universe could simply just be.
Completely self-contained.
Yeah.
Explained entirely by the laws of physics that govern it.
That's the hope. It suggests a universe that is neither created nor destroyed, but simply exists, governed by consistent physical laws. And what's more, the no-boundary proposal seems to naturally predict the kind of universe we see.
How so?
It naturally predicts that the universe would start off in a very smooth and ordered state, with the minimum possible non-uniformity allowed by the quantum uncertainty principle, those tiny inherent quantum jitters.
And then inflation takes over.
Exactly. The no-boundary condition provides the smooth starting point, and then it predicts that this state would naturally undergo a period of rapid inflation, amplifying those minimal quantum fluctuations to become the seeds for galaxy formation.
So all the complex structures in the universe, stars, galaxies, clusters, maybe even us, could ultimately be traced back just to the laws of quantum gravity via the no-boundary condition and the fundamental uncertainty principle of quantum mechanics.
That's the incredibly ambitious and elegant goal, yes. A universe entirely explained by physics from start to finish, with no arbitrary inputs needed.
That is an absolutely astonishing concept.
Yeah.
A self-contained universe born from quantum jitters. But it leads to another intriguing question, one that probably sparks a lot of late-night scientific debates. If the universe were to eventually stop expanding, maybe billions of years from now, and actually start contracting, would time run backward?
The collapsing universe scenario.
Yeah. Would broken cups suddenly jump back onto the table and reassemble themselves? Would we start remembering the future and forgetting the past?
That's a fascinating scenario, isn't it? And it was an idea that was initially considered even by the very scientist Stephen Hawking, whose work we're largely drawing on.
He thought time might reverse.
Early on, there was speculation that if the universe were to reverse its expansion and begin contracting, perhaps the thermodynamic arrow of time might also reverse. Disorder would start decreasing towards a final big crunch.
And that would lead to those weird science fiction possibilities.
It would. If entropy started decreasing, you could theoretically have situations like you described. The source mentions a thought experiment. An astronaut falling into a black hole, which is like a small collapsing universe, might be able to win at roulette by remembering where the ball will land before it stops spinning, because their future would become their past.
Wow, that's quite a thought. Winning roulette by remembering the future inside a black hole.
Right.
But it turns out that wasn't correct in the end. Time wouldn't actually run backwards.
No. Later, more rigorous calculations, including work by Hawking himself and others, show that this initial intuition was likely wrong. Even in a contracting universe or inside a collapsing black hole, the thermodynamic arrow of time would almost certainly not reverse. Disorder would continue to increase.
So even in a collapse, things would still get messier.
Yes. The future would still look very different from the past. Broken cups would stay broken even as the universe rushed towards a big crunch. The conditions required for entropy to decrease just don't seem to arise naturally, even in a global collapse.
Okay, so no time travel by universal collapse. That's maybe reassuring.
Perhaps, but it also highlights a really crucial aspect of how science progresses. The willingness to admit mistakes and revise ideas based on new calculations or evidence.
Right.
As the source points out, acknowledging when you were wrong, like Einstein famously did with his cosmological constant, which he initially introduced to keep the universe static and later called his biggest blunder when expansion was discovered, is absolutely essential for advancing knowledge. It's not a weakness, it's a sign of scientific integrity and strength, rather than stubbornly clinging to outdated ideas just because they were yours.
That's a great point. Science corrects itself.
Right.
Okay, we've journeyed from black holes that aren't quite black to the universe's explosive birth and rapid expansion, the curious nature of time's arrow, and even a universe without a beginning. It feels like we've touched on some incredibly profound truths, or at least the theories searching for them. But scientists, as you mentioned, are chasing an even bigger prize, aren't they? A single theory that explains, well, everything. The holy grail of physics.
That's right. The ultimate goal for many theoretical physicists is the discovery of a theory of everything.
What does that actually mean, a theory of everything?
It essentially means finding a single, complete, consistent theoretical framework that fully explains and links together all the fundamental forces and particles of nature. It would need to unify general relativity, our theory of gravity, and the large-scale structure of the universe.
Right, Einstein's theory.
With quantum mechanics, which describes the other three fundamental forces, electromagnetism, and the weak and strong nuclear forces that govern the world of atoms and subatomic particles.
So merging the very big with the very small.
Precisely. These theories are incredibly successful in their own domains. Gravity for planets and galaxies, quantum mechanics for atoms and particles. But they currently don't play well together. They use different mathematical languages and concepts, and they clash dramatically when you try to apply them both in extreme situations, like inside a black hole, or at the very instant of the Big Bang. A theory of everything would resolve these conflicts and provide one unified description.
And this quest, it's had its share of false dawns, hasn't it? Times when scientists thought they were really close to the final answer, only to discover whole new layers of complexity they hadn't anticipated. It sounds like the universe always has another trick up its sleeve.
It certainly seems that way sometimes.
Yeah.
History is littered with examples. At the beginning of the 20th century, some prominent physicists believed physics was essentially complete, maybe just needing a few decimal places refined. They thought everything could be explained by classical mechanics and electromagnetism, properties of continuous matter like elasticity.
And then came relativity and quantum mechanics.
Exactly. Atomic structure, quantum leaps, the uncertainty principle, it completely revolutionized our understanding, revealing a bizarre probabilistic reality at the smallest scales. Later, around 1928, after Paul Dirac discovered his famous equation describing the electron, the physicist Max Born reportedly said he thought physics would be over in 6 months.
6 months, that's bold.
Very bold. The hope was similar equations would quickly be found for the proton and other particles. But then the neutron was discovered, followed by a whole zoo of unexpected new particles and the realization of new nuclear forces, shattering that optimism completely. It's been a continuous process of discovery, often revealing deeper, stranger layers.
So what stands out to you based on the sources as the biggest hurdles right now in finding this ultimate unified theory? What are the main roadblocks?
The primary technical hurdle, the one that really bedevils attempts to combine gravity and quantum mechanics, is what's often called the infinity problem, particularly when you try to quantize gravity itself.
Infinities again, like inside black holes.
Similar mathematical nastiness, yes. Quantum mechanics tells us that even supposedly empty space isn't truly empty. It's the seething cauldron of virtual particle-antiparticle pairs, constantly popping into and out of existence, a sort of quantum foam.
Right, the ghostly particles.
Well, according to quantum field theory calculations, these virtual pairs should carry an infinite amount of energy. If that were true, their gravitational effect, according to general relativity, would be infinitely strong. They would essentially curl up the entire universe into an infinitely small size.
Which clearly hasn't happened. So there's a colossal clash between the predictions of quantum field theory and general relativity when you try to combine them naively. The maths just breaks down and gives absurd infinite answers. So we have these ridiculous infinities cropping up in our equations, mathematical results that make no physical sense, and we desperately need a way to make them go away or cancel out somehow to get sensible answers.
Precisely. That's been a major driver of theoretical physics for decades. How do you tame these infinities? One attempt, back in 1976, was a theory called supergravity.
Supergravity. It sounds impressive.
It was an ambitious idea. It tried to extend general relativity by introducing a new kind of symmetry called supersymmetry, which proposed that every known fundamental particle has a hypothetical, heavier superpartner particle.
A superpartner? Like a shadow particle?
Sort of, yeah. A fermion, like an electron or quark, would have a boson superpartner, like a selectron or squark. And bosons, like photons or gluons, would have fermion superpartners like photinos or gluinos. The hope was that the infinities generated by the virtual loops of regular particles might be perfectly canceled out by infinities, with the opposite sign generated by the virtual loops of their superpartners.
Like positive infinities canceling negative infinities.
Exactly, like adding plus use and beat mal and hoping they neatly sum to zero, or at least a finite number. It was a very elegant mathematical idea, promising this deep symmetry between matter particles and force-carrying particles.
Did it work? Did supergravity solve the infinity problem?
Wow. The problem was, the calculations required to actually check if all the infinities canceled out in realistic versions of supergravity were incredibly, monstrously complex. So complex and error-prone that nobody could definitively prove for many years whether the theory was truly finite or still had residual infinities lurking. It was just too hard to calculate.
So supergravity stalled because it was too complicated?
Largely, yes. While supersymmetry remains an interesting theoretical idea that physicists are still looking for evidence of at places like the Large Hadron Collider, the initial hope that supergravity itself was the final answer faded. This led, in the mid-1980s, to a massive resurgence of interest in a different, even more radical approach. String theory.
String theory, okay. This is the one lots of people have heard of. It's the current leading candidate for a theory of everything, right? And it's based on a completely different idea what fundamental particles are.
Yes, that's right. String theory proposes a radical departure from thinking of fundamental particles, like electrons and quarks, as zero-dimensional points. Instead, it suggests that the most fundamental constituents of reality are tiny, one-dimensional vibrating strings.
Strings, like tiny guitar strings.
Sort of, but much more fundamental. Imagine them like incredibly thin, plank-length loops of string, or maybe open segments of string, vibrating in different ways. And crucially, the different ways these strings vibrate correspond to the different fundamental particles we observe.
So an electron is just a string vibrating one way, a photon is a string vibrating another way, a quark is yet another vibration pattern.
That's the core idea. All the different particles and forces emerge as different notes played by these fundamental strings. It's a potentially very elegant unification.
And how does this help with the infinities?
Well, think about how particles interact. In standard physics, point particles interact at a single point in spacetime, which leads to infinities in the calculations. But strings are extended objects. When they interact, they don't collide at a point. They smoothly merge or split.
Like the legs of a pair of trousers joining at the seam.
Exactly the analogy used in the source. This smearing out of the interaction point from a sharp point to a smoother joining of tubes, the world sheets traced by strings, naturally avoids the mathematical infinities that plagued point particle theories, especially when trying to include gravity.
So the stringiness automatically cures the infinities.
It appears to, yes. That's one of its biggest selling points. String theory seems to provide a mathematically consistent way to incorporate quantum mechanics and gravity without generating those nonsensical infinite answers.
That sounds amazing. And string theory has a weird history too, right? It wasn't originally invented for gravity.
Correct. It has a curious backstory. It was first developed back in the late 1960s as an attempt to describe the strong nuclear force, the force that holds quarks together inside protons and neutrons. The idea was that the force between quarks was like a stretched string or rubber band.
So it started with the strong force. How did it jump to gravity?
Well, the original string theory for the strong force had some problems, like predicting massless particles that weren't observed. But then, in 1974, physicists John Schwartz and Joel Shirk showed that one particular massless particle predicted by string theory had exactly the properties expected for the hypothetical quantum particle that carries the gravitational force.
Wow. So gravity just popped out of the theory.
It popped out naturally, yes, but only if the tension in these strings was astronomically high, much, much higher than needed for the strong force. This suggested string theory wasn't really about the strong force after all, but might be a fundamental theory of gravity and everything else. After being somewhat ignored for a while, This idea, combined with its potential to solve the infinity problem, led to a huge revival of interest in the mid-1980s, and it's been the dominant approach to quantum gravity ever since.
Okay, but this leads to that really important question, the one that always fascinates me and probably confuses a lot of people.
Yeah.
If string theory is right, and these tiny vibrating strings are the fundamental building blocks, the theory apparently requires that space-time has more dimensions than the ones we experience, like 10 or sometimes even 26 dimensions.
Yes, that's correct.
So where are they? Why don't we see these extra dimensions in our everyday lives? We only experience 3 spatial dimensions, up, down, left, right, forward, backward, and 1 time dimension.
This is indeed a major and initially quite perplexing feature of string theory. For the mathematics of the theory to be consistent and free of anomalies, it requires space-time to have more dimensions than the 4 we directly perceive. Usually 10 dimensions, 9 space plus 1 time for superstring theories, or even 26 for older bosonic string theories.
So what's the explanation? Where did the extra 6 or more dimensions go?
The leading explanation, going back to ideas from Kaluza and Klein even before string theory, is that these extra dimensions are curled up or compactified into an incredibly tiny subatomic space. We're talking about dimensions curled up into a shape with a size potentially around the Planck length, about a millionth of an inch.
Oh, okay, that's unbelievably small.
Yeah.
So small we just don't notice them.
Exactly. They're so tightly curled up that they're completely invisible to our current experiments and everyday experience.
Can you give an analogy for that? How can a dimension be curled up?
Think about a garden hose. From far away, it looks like just a one-dimensional line.
Yeah, just a line across the garden.
But if you get very close, you see it actually has a second dimension, the circular dimension around its circumference.
Oh, okay.
So the idea is that at every point in our familiar 4-dimensional space-time, there's actually a tiny, incredibly complex, curled-up space existing in these extra dimensions, far too small for us to perceive directly. Another analogy often used is the surface of an orange.
The orange again. Okay.
From a distance, the orange looks like a smooth, 2-dimensional surface, ignoring its overall 3D shape for a moment. But if you were a tiny ant walking on it, you'd see it's actually curved and wrinkled with lots of tiny bumps and dips.
Representing the extra dimensions.
Exactly. Those tiny, complex structures are like the curled up extra dimensions. So on the incredibly tiny scales relevant to fundamental strings, space-time might be 10-dimensional and highly curved in complex ways. These curled up shapes are called Calabi-Yau manifolds, and there are zillions of possibilities. But on the large scales we experience, it looks effectively 4-dimensional and relatively flat.
Got it. So the extra dimensions are hidden because they're microscopic. And if this picture is correct, does it mean we can't use them for sci-fi stuff, like taking shortcuts through higher dimensions to travel between stars?
Unfortunately for sci-fi fans, probably not. If the extra dimensions are curled up to the Planck scale, they're far, far too small to navigate with anything macroscopic like a spaceship or even an atom. So those kinds of hyperspace jumps are likely off the table if this compactification idea is right.
Okay, maybe a bit disappointing for space travel dreams. But it raises another critical question, looping back almost to our earlier discussion. Why? Why did only 3 spatial dimensions and 1 time dimension apparently flatten out and become large and observable, while the other 6, or whatever the number is, remain tightly curled up and hidden? It seems like a very specific, maybe even arbitrary configuration out of all the possibilities.
That is a crucial question, and it brings the anthropic principle potentially back into play, but this time may be applied to the dimensionality of space itself.
Ah, the anthropic principle again. So the argument is that maybe only a universe with 3 large spatial dimensions allows for observers like us to exist.
Precisely. The argument, as laid out in the source material, explores what life would be like if the number of large, uncurled spatial dimensions were different.
What if there were fewer than 3? Like a 2D flatland universe?
Well, complex life as we know it seems impossible in fewer than 3 spatial dimensions. Think about a 2-dimensional being. How would it eat and digest food, its digestive tract would have to run all the way through it, essentially dividing it into two separate halves.
No, yeah, that wouldn't work.
And complex circulation systems or nervous systems would also be topologically impossible without crossing paths and blocking things. They'd be fundamentally limited in their biological complexity and function.
So no actual two-dimensional beings having a sophisticated chat over chai in Flatland.
Yeah.
Sounds pretty restrictive biologically.
Chuckles. Not effectively, no.
Yeah.
Their existence would likely be far too precarious and simple to allow for intelligence as we understand it.
Okay, so less than 3 is bad for life. What about more than 3 large spatial dimensions? Say 4 space dimensions plus time.
That also seems to lead to big problems for life. The issue is how forces like gravity and electromagnetism behave in higher dimensions. According to physics, the strength of gravity between two objects would fall off much more rapidly with distance in, say, 4 spatial dimensions than it does in our 3. It would follow an inverse cube law instead of an inverse square law.
And what would that mean?
It would mean stable planetary orbits, like the Earth going around the Sun, would likely be impossible. The orbits wouldn't be stable ellipses. Planets would either spiral into their star or fly off into space very easily.
So no stable solar systems.
Probably not. And the Sun itself, our star, might also be unstable in higher dimensions. The balance between gravitational pressure pulling it inwards and the nuclear fusion pressure pushing outwards is very sensitive to the dimensionality. Stars might either collapse into black holes too quickly or just fall apart. Either way, you wouldn't get the stable, long-lived stars needed to support life's evolution over billions of years.
Wow. And does the same apply to atoms?
Yes, similar arguments apply to the electrical forces holding atoms together. Stable atomic structures might not be possible in more than 3 spatial dimensions, meaning chemistry as we know it couldn't exist.
So the very conditions for stable matter, stable stars, stable planets, and ultimately any kind of complex life remotely like us seem to crucially depend on having exactly 3 large spatial dimensions, plus 1 time dimension.
That's the essence of the anthropic argument regarding dimensionality. We observe 3 large spatial dimensions because, according to our understanding of physics, that might be the only dimensional configuration among those possible in string theory, where intelligent observers capable of making such observations could possibly evolve.
It's a powerful, almost chillingly self-consistent argument for why our universe has the specific large-scale properties it does. A universe tailor-made, or at least self-selected, for us.
It really is. It shows this remarkable, deep convergence between the fundamental laws of physics and the necessary conditions for life to emerge and persist.
So let's bring it all together. Where are we now in this truly epic quest for a complete theory? This ultimate understanding of the universe. After centuries of incredible scientific progress, are we finally closing in on the finish line, or is there maybe still an infinite horizon of discovery stretching out ahead?
When it comes to the ultimate fate of this search for a complete theory of everything, the sources we've been drawing from outline 3 broad possibilities.
Okay, what are they?
Possibility 1. A complete, unified theory does exist. A single, elegant set of fundamental principles and equations that describes everything in the universe, and we will eventually discover it, assuming it's hard enough and our experimental technology continues to advance.
The optimistic scenario. We find the final theory. What's number 2?
Possibility 2. There is no single ultimate theory. Instead, there might be just an infinite sequence of increasingly accurate theories. Each new theory refines the previous one, explains more phenomena, works at higher energies, but there's never a final, all-encompassing answer. We just get better and better approximations forever.
Like peeling an infinite onion. Always another layer.
Exactly like peeling an infinite onion. And possibility 3 is that there is no theory at all. Events in the universe are fundamentally random and arbitrary, not governed by underlying laws.
Okay, but surely modern science rejects that last one.
Oh, absolutely. The incredible success of physics, especially quantum mechanics, in predicting phenomena with amazing accuracy within the bounds of the uncertainty principle, makes the idea of a completely lawless, arbitrary universe untenable. So we're really choosing between possibility 1, a final theory exists, and possibility 2, an infinite sequence of theories.
And which one seems more likely? Based on history, that second possibility, the infinite sequence, seems to align pretty well with our experience so far, right? With all those false dawns in physics where people thought they had it all figured out, only to find new, deeper layers of complexity.
It does. It certainly aligns well with the historical pattern. Every time we've pushed the boundaries of energy or precision with experiments, we've often discovered new particles, new forces, new phenomena that weren't predicted by the existing theories, forcing us to develop more refined ones. The standard model of particle physics, while incredibly successful, still leaves many questions unanswered.
So maybe the onion is infinite.
It's possible. However, despite this history, the source material suggests there's still a strong sense of cautious optimism among many theoretical physicists today. There's a feeling that maybe, just maybe, we are nearing the end of the search for the truly ultimate laws of nature. This leans towards the first possibility that a complete, elegant theory does exist, and we might be on the right track, perhaps with something like string theory or its descendants like M theory.
Cautious optimism, I like that. And what would it truly mean for humanity, for all of us, if we actually did discover this ultimate theory of the universe, this complete recipe for the cosmos? Would it change everything?
It would be a monumental achievement, arguably the pinnacle of human intellectual endeavor, the culmination of centuries, even millennia of scientific inquiry stretching back to the ancient Greeks and beyond. It wouldn't just mark the end of a long and glorious chapter in the history of science. It would also fundamentally revolutionize the ordinary person's understanding of the laws that govern the universe and our place within it. Think back to Newton's time. An educated person back then could plausibly grasp the whole of human knowledge, at least in broad outline.
Right, science was more accessible then.
Exactly. But since then, the sheer pace and complexity of scientific development has made that completely impossible. We live in a world of extreme specialization and fundamental physics, particularly things like quantum field theory and general relativity, often seem utterly inaccessible and counterintuitive to most people.
So this ultimate theory, it wouldn't just be for the specialists in their ivory towers.
If found, the hope is that its fundamental principles, once grasped, should eventually be understandable, at least in broad outline, by everyone, not just a handful of scientists. It might take time to digest and translate, but the core ideas should be communicable.
And what would that allow?
It would allow all of us, the general public, to take part in the grand discussion about the deepest questions. Why does the universe exist? Why is it the way it is? If we find the answer to that, if we could truly understand the fundamental principles that govern everything from the smallest subatomic particle to the largest clusters of galaxies, well, the source describes it as the ultimate triumph of human reason.
The ultimate triumph of human reason.
For then, it suggests, we would truly know what some have metaphorically called the mind of God. Not necessarily in a religious sense, but in the sense of understanding the fundamental logic and blueprint of reality itself.
Wow. Okay, what a journey we've been on. We started with black holes that aren't quite black, realizing they might actually glow and evaporate due to quantum effects. We then zoomed out to explore the universe's explosive birth of the Big Bang, its incredibly rapid inflationary expansion, and the surprising way that tiny quantum jitters could have become the seeds for all the galaxies we see. We've even tried to unravel the curious, arrow-like nature of time itself, why we remember the past and not the future, and pondered a universe that might not need a traditional beginning at all thanks to quantum gravity. And all of this leads to that ongoing, incredibly ambitious quest for a single theory, a theory of everything that binds all these disparate pieces together. It's been a truly mind-bending exploration.
It really has, and it's important to remember these ideas we've discussed today, Hawking radiation, inflation, string theory, the no boundary proposal, they aren't just abstract mathematical games confined to textbooks or physics journals.
Right.
These are the profound theories that physicists are using to try and explain why we are here, how the universe works at its absolute deepest levels, and perhaps even the very nature of existence and reality itself. They really push the boundaries of what we can even imagine, and they demonstrate the incredible power of human curiosity, mathematics, and reason to probe the cosmos. So, let me leave you, our listener, with a final thought to ponder. If we do someday discover a complete theory of everything, this grand unified recipe for the cosmos, what does that tell you personally about the fundamental nature of reality itself? Does discovering such a complete and potentially elegant underlying structure make the universe feel more like a grand, intricate design? Like a magnificent blueprint laid out, just waiting for us to fully decipher it? Or does it make it feel more like a magnificent, perhaps even beautiful accident, the inevitable outcome of a few incredibly simple yet powerful fundamental laws that just are, without needing any deeper purpose or designer?
That's a deep question. Design or accident, based on elegant laws. And maybe another way to think about it, if we could truly understand that mind of God, as you put it, through the elegant language of science and mathematics, what new questions would that realization open up for humanity? Questions about our philosophy, maybe our purpose, our ultimate place within this vast, intricate, and possibly self-contained cosmos.
Exactly. The end of one quest often marks the beginning of entirely new ones.
Keep asking those questions, keep exploring, and we'll keep diving deep into the cosmos with you.